My name is Matthew Marco, and I researched how the intermolecular van der Waals forces, the forces that allow liquids to stick together and become viscous, can influence the progression of entropy. This research, if I am correct, means that by using high pressure and supercritical fluids, the efficiency of a heat engine can be improved. One fundamental law of nature is that heat always flows from hot to cold. This is obvious. If you have a mole of fast-moving molecules colliding with slower molecules, then the kinetic energy of the hotter, faster molecule's motion will transfer to the colder, slower molecules. The second law of thermodynamics states that, since heat can only flow from hot to cold, all heat transfer processes eventually reduce the overall temperature differentials in the universe until eventually everything is the same temperature. As the number of a temperature differential decreases, or the greater the disorder, the more entropy that exists. Knowing that heat can only flow from hot to cold, the Carnot heat engine cycle is a theoretical cycle to calculate the maximum possible efficiency of a heat engine using an ideal gas as the working fluid, and no temperature differentials during heat transfer. In reality, all heat transfer requires some temperature differentials, but for the sake of this theory, assume the heat transfer occurs over an infinitely long time period at virtually no temperature differential. In the Carnot cycle, the ideal gas first is compressed within a large temperature sink, maintained at a constant cold temperature, where heat leaves the working fluid equal to the energy applied by the piston. Next, work is spent by the piston to compress the fluid further, but with no heat transfer happening. The temperature rises. Next, this hot temperature expands at a constant hot temperature, receiving a heat input with an equal work output. Finally, the hot fluid expands with no heat transfer until it returns to the original volume and cold temperature. In this cycle, heat transfer only occurs during isothermal or constant temperature compression and expansion, ensuring that there is no significant temperature differential exists during heat transfer, and thus no entropy is generated by this fully reversible cycle. The Carnot cycle assumes an ideal gas as the working fluid, where the pressure is inverse proportional to the specific volume at a constant temperature. Work is defined as the integration of pressure over a changing volume, and therefore for an ideal gas undergoing isothermal or constant temperature compression, the work input and the heat output is equal to the product of the gas constant R, the temperature T, and the natural log of the ratio of the volume. Also, in an ideal gas, the work energy of compression or expanding the fluid will be proportional to the constant volume specific heat multiplied by the change in temperature. Ergo, all work out to lower the temperature will equal the work input to raise the temperature. This slide shows the calculated work and heat transfer for all four changes in state of the ideal gas Carnot cycle. W represents the work, and Q represents the heat. The efficiency of a heat engine is defined as the work output obtained from a given heat input. Due to the conservation of energy, the work output is equal to the difference between the heat input and the heat output. Therefore, the efficiency can also be defined as 1 minus the ratio of the heat output over the heat input. Using the values obtained in the earlier slide, the efficiency of an ideal gas Carnot cycle, which generates no entropy and is entirely reversible, is equal to 1 minus the ratio of the cold temperature over the hot temperature. This value is known as the Carnot efficiency. A Carnot heat pump is the exact same cycle in reverse. Ergo, the coefficient of performance, or the heat output over a given work input, is simply the inverse of the Carnot efficiency. Let us assume, as a thought experiment, that we had a heat pump connected to a heat engine, where the heat pump's output was the heat engine's input, and the work output of the heat engine powered the heat pump. If the efficiency of the heat engine exceeded the inverse of the coefficient of performance of the heat pump, then the work output of the heat engine will exceed the work input of the heat pump, and a net total work output would be generated simply by heat from the ambient temperature. No temperature differential will be needed. This, by definition, is a Type 2 perpetual motion machine, violating the second law of thermodynamics. For this to happen, however, assuming the cold temperature of both the heat engine and the heat pump are the same, the hot temperature of the heat pump has to be equal to or greater than the hot temperature of the heat engine. With this fact, under the ideal gas Carnot efficiency limit, the heat engine's efficiency cannot exceed the inverse of the heat pump's coefficient of performance. Everything discussed so far has been assuming ideal gases as the working fluid. An ideal gas is one that is less dense such that there is no effect of the van der Waals intermolecular forces. A real fluid, however, is dense enough such that the polarities of the molecules attract and repel each other. As the density of a fluid increases, at first the attractive component of these forces will reduce the pressure, but as the density gets greater and greater, the pressure will eventually get greater and greater. Of course, all real fluids, if they are sufficiently expanded, will eventually become an ideal gas. An equation of state is a function that gives one the pressure for a given temperature and specific volume or density. We all know the ideal gas law, but for real fluids, there are numerous empirical equations published. Two well-established equations of state are the Riedler-Kwong and the Peng-Robinson. In both of these examples, the first component is similar to the ideal gas. The coefficient of B represents the repulsive force of the molecules as the fluid reaches the most extreme densities. The second component represents the pressure reduction from the attractive component of the van der Waals forces. There are two features we can observe of the van der Waals attractive force from the empirical equations of state. The first is that, with expanding volume, the attractive force quickly becomes negligible as the real fluid becomes an ideal gas. Second, the attractive force is temperature dependent. The van der Waals attractive forces, which reduce the pressure of a real fluid, both increase with decreasing temperatures and increase with increasing densities. With an ideal gas, where the van der Waals forces are negligible, the total internal energy is effectively the sum total of the kinetic energy of the motion of all of the molecules. Temperature is simply a representation of the square of the average molecular velocity. With a real fluid, however, heat energy is needed to overcome the changes in potential energy of the molecules. The internal energy will inherently decrease with increasing densities, as the molecules are in closer proximity and thus will need more energy to be expanded back. The intermolecular potential energy of a real fluid is thus the integration of the reduction in pressure from the van der Waals forces, or delta P, from the equation of state, over the change in volume. In most books and papers on thermodynamics, this original formula for the change in internal energy U was established to ensure the second law is maintained and the total increase of entropy to the universe always remains positive. The second equation for the change in internal energy U was obtained empirically by looking at the energy needed to boil numerous different liquids. The change in internal energy delta U can simply be found by taking the energy needed to boil a liquid, or the enthalpy of vaporization delta H, and subtracting the product of the pressure, which remains constant, and the change in volume from a liquid and a gas. With this, an experimental measurement for the change in internal energy of an expanding real fluid is obtained. Both the original and the empirical formula has been demonstrated to match well for a boiling liquid. The question then to ask is simply, which is the correct formula for all applications? The original formula created to maintain the second law of thermodynamics, or the empirical equation based off of the potential energy change of the van der Waals forces. As a demonstration, the two formulas for the internal energy will be compared with a theoretical Stirling cycle heat engine. A Stirling cycle is similar to the Carnot cycle, except instead of compressing and expanding the gas with no heat transfer, the gas is heated up and cooled down at a constant volume. Simply put, you have a constant cold temperature compression, heating at a constant compressed volume, constant hot temperature expansion, followed by cooling at the constant expanded volume. Using carbon dioxide as the working fluids, operating between 32 and 82 degrees centigrade, the thermodynamic properties are tabulated, and the internal energies and the heat transfers are compared using both the empirical equation, listed as calc, as well as the original formula using the National Institute of Standards and Technology, or NIST, webbook. As expected, the efficiency of the original formula using the NIST webbook results in an efficiency below that of the Carnot efficiency. If the empirical equation is correct, however, then it is theoretically possible to exceed the Carnot efficiency using a real fluid, due to the temperature dependence of the van der Waals forces. The van der Waals attractive force will both reduce the work input and the work output, but because these forces are stronger at the colder temperatures, the reduction in costly work input will be greater than the reduction in beneficial work output, allowing for a net increase in the thermodynamic efficiency to theoretically exceed that of the Carnot efficiency. It is clear we have two equations for the internal energy of real fluids, one developed to maintain the second law of thermodynamics, and the other obtained empirically based on integration of the reduction in pressure from the van der Waals attractive forces. Which equation for the change in internal energy of a real fluid is correct? This question must be determined with an experiment. The experiment I conducted to measure the change in internal energy of a real fluid involved two 5-pound carbon dioxide cylinders manufactured by Luxfer and 3.4 liters each. They were connected together at the valve by a manifold, with a ball valve as well as a separate valve for disassembly. In addition, each cylinder was connected with a thermocouple as well as a third thermocouple for the manifold. Finally, this apparatus was kept in an insulated chest. When an ideal gas rapidly expands, such as via the sudden opening of a valve, then the pressure will decrease proportional to the volume increase. Assuming there is no heat transfer, the temperature and the internal energy of the ideal gas will remain constant during the expansion. The entropy will inherently increase as this process is reversible. If a real fluid were to rapidly increase, such as via the sudden opening of a valve, in addition to the pressure decrease, the temperature will also decrease. Assuming there is no heat transfer, the total internal energy will remain the same. However, the potential energy will have to increase as the molecules will overcome the van der Waals attractive forces as the fluid expands, and therefore the kinetic energy, what we call the temperature, will have to decrease to make up the difference. This is known as the Joule-Thomson effect. In the context of a practical experiment, when a real fluid, such as liquid carbon dioxide at room temperature, expands, its temperature decreases. Later on, the temperature of the containers will decrease, increasing the temperature of the expanded fluid until the temperatures of the carbon dioxide and the aluminum cylinders equalize. If the heat capacity of the two cylinders and the manifold is known, then the heat input to achieve the new volume and temperature can be determined. To determine the heat capacity of the gas cylinders and the manifold, the item was cooled in a commercial freezer to approximately -20 degrees centigrade. Next, water was placed in a bag within the insulated chest, where the mass and the initial temperature of this water was measured beforehand. To start the measurement, the cold cylinder or manifold was placed in the insulated bag of water for 60 minutes, well after the temperature is settled. Knowing the specific heat capacity of liquid water, the ratio of the heat input from the water into the item under test, divided over the change in temperature, is used to obtain the heat capacity of the cylinder and the manifold. After the heat capacity of the cylinders and the manifold were successfully collected, the experiment can commence. For each individual trial, the first step is to measure the mass of carbon dioxide in the first cylinder. This is achieved with a simple calibrated scale, as well as collecting the mass of the cylinder while empty. Next, the cylinders are assembled together with the manifold and placed in the insulated chest. The initial temperatures of the cylinder and the manifold are collected via the thermocouples. Next, the ball valve on the manifold is opened and the insulated chest is rapidly closed off. When the temperatures of the thermocouples have settled, the new colder temperatures are recorded. Finally, the cylinders are separated and the mass of carbon dioxide in each individual cylinder is recorded on the scale. With this data and the knowledge of the heat capacity of the cylinders and the manifold, the heat input into the carbon dioxide from the test can be determined. The ultimate goal of this experiment is to compare the experimental heat input with the heat input expected with the empirical equation, as well as a NIST webbook which utilized the original equation for the change in internal energy of a real fluid. This process yielded heat inputs for 25 separate and unique trials. Looking at this data, the empirical equation based on the theory of the potential energy overcoming the van der Waals forces matches the experimental data better than the NIST webbook. My theory for the change in internal energy of a real fluid matches better than the NIST predictions in correlation, the mean, the median, and the standard deviation of the error. One can also clearly see the improved match in the figure on the left. This experimental data shows that the internal energy of a real fluid should be determined by integrating the pressure reduction from the van der Waals attractive forces, rather than rigidly assuming the internal energy would automatically and inexplicably adjust itself to fit within the second law of thermodynamics. Second, this experiment suggests that the Carnot efficiency might not in fact be the absolute theoretical best when dealing with real fluids. Finally, this experiment suggests that it is worth considering real fluids in a practical heat engine such as a Stirling cycle to try to further boost the thermodynamic efficiency and extract more useful work from a heat source. I encourage everyone to read the paper I published on this work in the peer-reviewed journal Nature Scientific Reports to better understand my theory and experiment. If you have any questions, if you would like to try to repeat this experiment, or if you wish to see copies of my analysis and raw data, please do not hesitate to email me, mattdmarco@gmail.com. Thank you very much for listening to my presentation.